Yo guys, what is up? Welcome back to today's video, and we will be discussing bone growth as well as types of synovial joints, or the shapes of the synovial joints, right? So in the previous video that we did, we covered everything about joints, like the types. So you've got fibrous, cartilaginous, and synovial joints, and we covered their composition as well. So they're made up of DFCT, which is dense fibrous connective tissues, and cartilage, right? So cartilage can be split up into hyaline cartilage and fibrocartilage. Hyaline can also be called articular. For DFCT, dense fibrous connective tissues, they can be split up into ligaments, tendons, and joint capsules, right? We also covered we drew the structure of a knee and of the different ligaments present in a knee, and as well as the types of joints and their examples and what they're for, like their functions and purposes. So in today's video, we're going to be expanding on that more, and we'll be specifically covering synovial joints, right? Shapes, and also dab in a little bit of bone growth, just to fill up the content basically. So bone growth is, imagine you're born, right? So you're a fetus. Now when you're a fetus, you don't have bones just yet, but you have cartilage, right? So imagine this is your bone. Let's say this would be a bone right here. And after about 6 weeks after you're born, your bone will start, or after 6 weeks of fertilization, my bad, not born, your bone, your cartilage will start a process called endochondral ossification, right? So the cartilage is being ossified or turned into bones from the inside. That's why it's called endochondral. All right, so imagine this is your cartilage of the little fetus in the womb, right? It will start over here. The process will start in the middle. This is called the primary ossification center. Ossification center. Right, it will start in the diaphyses, or the diaphysis of the cartilage. Right? This is your primary ossification center, and this is where osteoblasts are found, right? Because osteoblasts are cells that blast out bone matrix or produce bone matrix, or an ECM or extracellular matrix, same thing, right? Which makes it a bone. So minerals like calcium, like hydroxyapatite, and calcium carbonate ions and minerals will be deposited here, and this is when ossification starts in the middle for around from week 6 to week 10, right? And then after that, after week 10, secondary ossification center will appear, right? So now basically this, so what happens is that your bone will kind of recruit. So this is like your blood vessels. These are your blood vessels, and also osteoblast, right, into the primary ossification center. And once you have that, you form this like structure over here with your blood vessels in here, right? Because one of the big differences between cartilage and bone is that bones are vascular and cartilages are avascular, so they don't have a blood supply. That's why you need to add blood vessels into cartilage at this point in time. All right, and then so depending on the different position of the bones, right, ossification will start at different times, but generally it will start 6 weeks after fertilization. All right, so that's your primary ossification center. And then this goes on between from week 6 to week 10, where the different bones will start to be ossified, right? Then after week 10, a secondary ossification center will appear, and the secondary centers will be in your epiphysis or epiphyses, right? So it'll start growing here. Imagine you have this area as well. Let me just draw that out, actually. Tight areas now here. Right, and then you've got this area here as well. So these guys are your second center, secondary ossification center. All right, and this is your epiphyses. Right, this right here is your growth or epiphyseal plates. Right, and this helps with bone growing vertically, because as you're growing more, so I'll draw it down here. So as you're growing, more cartilage. So here, what for this diagram up here, what I'm shading is the bone, or the osteos, this bone cells basically. The clear or translucent bit is the cartilage. Down here, what I'm shading is the cartilage, right? And what I am leaving unshaded is the bones, basically. Or specifically in this case, I'm just trying to highlight the epiphyseal plate, right? And so as you grow, more cartilage is being added on top of here. More cartilage is being added to this epiphyseal plate on the epiphyseal side of things, right? So you're being added onto this side. Well, the cartilage on this side, on the diaphyseal side, is being actively ossified. So over time, your bones will grow longer, but your growth plate size will remain the same, because more is being added, more cartilage is being added on top near the epiphyseal side, and the cartilage of the growth plate in the diaphyseal side is being ossified. So over time, your bones will grow longer and longer until you're an adult, right? And that's when your diaphysis and your epiphyses will merge, and you'll form what is called the epiphyseal line. Basically, this is your medullary cavity, and this is your epiphyses, of course. Epiphyses down here as well. This right now is your cancellous bone, basically. Right. So down here. So this is when puberty starts, right? So as puberty starts, the diaphyses will start fusing with the epiphyses, and the epiphyseal plate will be converted into, or it will disappear and form the epiphyseal line. And this is due to ossification, basically. So you still have a little bit of cartilage on top of here at the top, each end of the bone, to help with movements like frictionless movement. But overall, these parts have merged, basically, and there's no cartilage in between them. It's just bone. All right, this in the epiphyses, there will be cancellous bone. This is your medullary cavity where all your osteoblasts are found, right? So, because what I'm saying is, so for example, sorry, I forgot to mention, but for this specific diagram here, where more cartilage is added on top of this epiphyseal growth plate, the cartilage cells down here at the bottom of the plate is being ossified, because the osteoblast in the medullary cavity is moving upwards and ossifying or depositing the the bone matrix into here and turning these cartilage cells into bones, basically. And over time, the medullary cavity will grow larger and larger until it reaches its mature size. And this is when it stops, and there's no cartilage in between them anymore. It's just bone. This is when you know puberty has started and epiphyseal plate is being formed, right? So this is basically everything about bone growth. And again, bone homeostasis or homeostasis is dependent on the activity of osteoblast and osteoclast, which I have covered in another video. So please go check that out. So let's cover the different shapes of synovial joints. All right, so what we'll do is actually turn it sideways. So the first shape we have is planar. So there's 6 different shapes, by the way. First shape is plane. It's when you have 2 planes like this pushed together, right? So I'll try and draw like a visual guide for you guys. So the first one is plane. Second one is saddle. Third one is ellipsoid. All right. Fourth one is hinge. Fifth one is pivot. And sixth one is ball and socket. So I know my spacing is not that great because I was just estimating them, but here we go. So a plane will kind of look like this, if you can like imagine what it look like. So imagine this is your thing. So this is two of the bone surfaces. And I'll shade in them so it's easier for you guys to figure out which one's which. This one right here, the base at the bottom. These are two different bones basically, and they have a flat surface of contact. So this is plane. For a saddle, imagine you have, so for hip plane, it's like this when you push 2 of your hands together, so they can move this in these directions, so they can move in this plane. So it's multi-axial because it can slide, it can glide, it can rotate, right? It can slide forward, backwards, left, right. It can rotate as well. So that's why it's multi-axial, right? Multi-axial. And the movements are sliding in, all different directions, plus rotation, right? And let's see, an example would be your intercarpal and intertarsal joints. Intercarpal joints, right? So for example, in your fingers over here, between your carpals will be the carpals around here, and that's how you know those basically joints like that, right? And now let's talk about, so these would be I can kind of slide them. It's really hard, so you can try in your body, right? You can wiggle your arm, you can wiggle your different body parts around to see, which one is, which you can try and like determine which one is which joint is different types. So normally synovial joints are the joints that have the most amount of movements, as I said earlier, or they have a lot of movements. They're quite mobile. That's why any joints you can move freely in your body to a certain degree is a synovial joint. And you can try and make different movements and try and classify which one are them, basically, and really see how they go. So imagine your intercarpal joints. It's kind of like this, right? So between your phalanges, this one right here, there's one here. So between these, you see these lines on your fingers, they're roughly where the joints would be. So those are the interphalangeal joints, and intercarpal joints would be around your wrist or in your palm sort of area, where you can rotate, you can sort of glide it. So that's where your intercarpal joint is. And the next type is the saddle. So imagine you've got two cups like this against each other. How I'd remember this is I'd imagine a person sitting on a horseback. So the horseback is kind of like this, and the person's leg is kind of like this to this, right? You can roughly imagine this, the person's leg is on the other side of the horseback, just like this. If I were to draw it 3D, like that. So that's roughly one way of thinking about it. So I would draw it like this. I know it's not the best of drawing, just bear with me here. So imagine it like that. Like kind of this shape of here, like 3D yin yang. That's how I would say it. This thing is again multi-axial because it can do a lot of different things, right? So it can perform flexion, extension, abduction, and adduction, right? So flexion is when you decrease the angle from the joint to your body, referring to the anatomical position. And extension is when you're increasing the angle. And abduction is when you bring it away from your body and backwards. So for example, imagine this side is the midline of my body, right? So more medial, the side is more lateral. I can do abduction like this, like abduction, or adduction, or flexion, and extension, hyperextension. So flexion, so bring it upwards, it'll slide back down like that. Or extension, so bring it back to the normal position. And hyperextension. So hyperextension only works with your knee and your leg, because that's the only thing you can try and do hyperextension in. So that's why it's multi-axial, and because it can do flexion, extension, adduction, abduction. So if you can perform these four movements, then of course you can perform circumduction. Circumduction is a combination of all four movements. So imagine if you hold out your arm, this, or your wrist, and you perform this circular motion. This is circumduction, because if you think about it, this is your anatomical position. The two of your palms are facing forward. This would be flexion, extension, abduction, adduction. So it's, if I twirl my wrist around like this is circumduction, combination of all four movements. And an example would be your intercarpal joint. Right. So now we move on to ellipsoid. And let's see, so ellipsoid, the shape is quite similar to ball and socket, but because it's elliptical, not circular or not spherical. So imagine you have this right here, like this is just like this. Imagine that, and then you have this. Right, so this would be the structure of ellipsoid. And on that note, a ball and socket will look a little bit more circular like this. And the thingy like that. Okay, so this is more circular, it's more elliptical. Right? So I like to imagine it like if you close your fist like this is ball and socket. But if you hold it like this is ellipsoid, right? So ellipsoid, the shape of the bone is elliptical, it's not spherical. Therefore, there is no rotation because you can't rotate this anywhere else. Whereas for ball and socket, it's perfectly spherical, so you can rotate it a lot of ways, right? So therefore, ellipsoid is biaxial, right? Biaxial because, or you can say biaxial is the same thing as multi-axial. In this case, multi. Let's just say multi, right? And because it can perform flexion, extension, adduction, and abduction, right? So therefore circumduction as well. So these guys are pretty similar, but the shape is just different. And an example of ellipsoid is your temporomandibular joint, TMJ. So between your jaw. So imagine if you open and close your jaw, that's the joint where you're opening and closing your jaw, like that. Then now you've got a hinge. Hinge is like a door hinge, for example. You just have this. Like, there's nothing too special about hinge. Like, for example, this would be hinge. Like, imagine it's just shaded, just like that. So it can move. It can. So imagine it's like this. It move up and down. So it's one directional, uniaxial, right? Because it can only move like that. Basically, it can only perform flexion and extension. And an example of that would be your ankle. Actually, I'll just write down here, just to avoid confusion. There you go. Ankle. All right, or let's say, well, ankle's not quite a hinge, but a more accurate term would be, let's say, your elbow. I'd say elbow is one. So it's elbow. It's more of a hinge type of joint. So it's basically, elbow is basically between the humerus and the ulna of your arm, or the interphalangeal joints. So between your phalanges of your arms, so it's these joints over here. They can only move in one direction, like that. So it's extension, flexion, extension, flexion, extension. And then you've got pivot as well. Pivot is again uniaxial. There's only one direction, same. So hinge and pivot is the only two uniaxial joints out there for synovial joints. So I had a brain fart. So imagine this is your joint. This is your hinge. So you can only perform rotation like this. Like imagine like that. You can't do anything else. The only movement is just rotation. So rotation. And you can find this in your radial ulnar joint. So basically a proximal radial ulnar joint. So again, in your forearm, like it's like around. When you twist your forearm like this is the only movement you can get. It's rotation, and the radial ulnar joint is it's about somewhere here. It's not where your elbow is. It's a bit forward of your elbow. It's when your radius crosses over with your ulnar when in pronation. So supine, when you flip it over, your radius crosses with your ulnar in pronation. And then you've got ball and socket, which is, again, this is the most mobile one of all, multi-axial. So this would be your shoulder, for example. So that you can basically perform all of these actions: flexion, extension, adduction, abduction, rotation, and therefore these four: circumduction. An example would be your shoulder and your hips, right? You can perform rotation. You can do a lot of things with your hips, basically. So that is, but the difference is hips has a deeper articulation and shoulder has a more shallow articulation. That's basically all about synovial joints and bone growth. Thank you for watching today's video, and I'll see you in the next one.